IIT Bombay, Mumbai, India. His research interests broadly include communication and signal processing, with emphasis on multi-resolution approaches. Dr. Gadre was the recipient of President of India Gold Medal from IIT Delhi in 1989 and the Award for Excellence in Teaching from IIT Bombay in 1999 and 2004. He is also the recipient of SVC Ayya Memorial Award, Srinivasan Medal for the Institution of Electronics and Telecommunication Engineers for contribution to education in electronics and telecommunication. He has guided sponsored research projects for organizations like Tata, Infotech, Texas Instruments, and numerous PhD, MTech dual degrees and BTech projects. Also, he is the guide of Dr. Manish Sharma sir. So I welcome you sir on behalf of IIT today.
Yeah, very good morning. Yeah. Can you hear me clearly?
Yes sir.
Oh. So, I start gentle now. Keep ready to see the presentation. Ready to see the presentation?
Yes sir.
Can you confirm is the presentation visible?
Yes sir, it is visible.
Okay. So now I go to the presentation. Right. And first and foremost, thank you for inviting me. Is my voice clearly audible?
Yes sir, your voice is clearly audible.
Oh, good. So, very good morning to all of you and a very warm welcome to this session. In fact, I have my PhD student currently. Manish has been, Professor Manish Sharma has been my aspiring PhD student, almost 9 years ago, graduated. And Kishore is my current PhD student, right? He's sitting with me. In fact, he is instrumental in putting this presentation together. It's the work that we are doing currently. My intent with this presentation is to give you a feel of how multi-resolution representation and deep learning come together for biomedical treatment. Kishore's PhD work is closely related to this theme. Although what we are going to present in this talk has to do both with Kishore's work and the work of one of my other current PhD students called Nitin Lakshmi Shah. So in fact, we have intentionally taken two examples or rather that way, three examples of biomedical applications. One of them is one-dimensional, related to fetal ECG, and the other relates to magnetic resonance imaging, MRI, which Kishore is working on. And fetal ECG is what my other PhD student Nitin is working on. So, without further ado, let me proceed to explain to you how multi-resolution principles can come together very famously with deep learning. Do you see the slide moving? Can you confirm?
Yes. Yes sir.
Yeah, the slide moving good. So, see, deep learning and convolutional neural networks, both of them that's there, and almost any student today would like to have something to do with deep learning. Maybe many of them, particularly those who want to work with convolutional neural networks. And understandably so, because they've revolutionized the machine learning industry, and when you have layers of CNN, they allow you to do quite remarkable things. And many of us are familiar with. Moreover, the fact that we have increased depth and width of deep convolutional neural networks, which is deep learning very several layers, and that would require computational power. So more and more complex architectures are possible. Naturally, all this comes at the cost of computational and storage resources. And another problem that comes in is that it's more and more difficult to understand what is happening. We find that the layers of CNS work wonders. When you have convolution followed by non-linearity and repeated layer after layer, it seems to work wonders, but all of it remains like a black box, which we find difficult to explain. Now, today that's why people have been seriously looking at explainability or interpretability in artificial intelligence. And there are many routes to that. One of the routes is to employ what we are aware of as fundamental signal processing principles and see if you can marry those signal processing principles with machine learning or deep learning to advance. So, in this work, that's what we aim to do. We want to use one specific dimension of signal processing, namely multi-resolution principles or time frequency method, and bring it together with deep learning for biomedical signals with some intent to bring in explainability and interpretability and to some extent economy. Why should you be doing multi-resolution analysis? I'm on the third slide. You see third slide, I'm just checking one or two slides to make sure the slides are moving. Manish, can you confirm that?
Yes.
Yeah, good. So why should we be looking at multi-resolution analysis as a paradigm? Well, we all know, many of us who might be in the signal processing domain are well aware of the importance of orthonormal representation of signals. The orthonormality brings with it a certain degree of canonical quality, non-redundant. So orthonormal representation improves pattern recognition. They bring what we call canonical features, they bring features that are non-redundant, and they also bring features which can be independently applicated. So orthonormality is very powerful tool. Now one class of orthonormal decomposition is the so-called wavelet analysis. Wavelets are compactly support the orthonormal wave functions, and the beauty of wavelets is that compactly supported means they are very often they can have finite extent in the time domain, the natural domain, and also a reasonable confinement in the frequency domain. So, see, you are looking, in fact, no, I am not waiting for full explanation of this, but many of us can appreciate that a lot of our signal processing or signal understanding or signal, signal interpretation tasks are not only in one domain. Let's take the example of audio. In audio, we want some kind of time analysis, but we also want some kind of frequency domain analysis. So a lot of now when you go deeper, you realize that even in the biomedical domain, a lot of applications are actually dual domain, not single domain. You need to look at both the natural domain, the transformed domain at once. And if you bring this principle, the principle of multi-resolution analysis, together with deep learning, there are many things to be gained. So these multi-resolution representations can be learned enforcing wavelet analysis in deep learning aspects. Let's look at how you would implement the wavelet multi-resolution analysis. You would do it with a discrete wavelet transform, which decomposes a signal into different scales of resolution using dilations and translations and orthogonal scaling functions and waves. So in principle, the DWT analysis uses a pair of filters, called quadrature mirror filters, to generate a direct multi-resolution representation. Again, here I can't possibly explain all this in great mathematical depth here in this talk. Some of us might be aware, but I'll try to give you an intuitive understanding of what we are doing here. So you see, what we are doing here is to think of representing. Is my cursor visible, Rahul? Manish? My cursor visible?
Yes, sir.
Okay. So, for column of cursor, actually, what you have with the input the two bands is essentially a discrete representation of the signal. A discrete representation of the signal as projected onto one of the subspaces of the space of finite energy function. So you have, of course, in all practical, for all practical purposes, it will only be finite energy functions when you want to analyze biological signals. It will also do more realistic signal analysis problems, where you really are dealing only with finite energy functions. So with the finite energy function, you could decompose, take a particular subspace of that of a class of finite energy function, which can be expressed in terms of one kind of function shifted in step. So, let me give you an example. You could make a piecewise constant approximation to a function by averaging the function over uniform intervals. And the average can be thought of as representing the function on each of those intervals. So this is one example of projecting a finite energy function onto a subspace of the space of onto a subspace of class of finite energy function. Right? So you can imagine the coefficient for these averages on each of those intervals being placed here as a sequence. And the sequence is subjected to the action of two filter bands, or two filters in a filter bank. A quote-unquote low-pass filter and a high-pass. Now, the low-pass filter generates the approximation coefficient after destination for downsampling by 2, and the high-pass filter generates the decay. Again, this low-pass and high-pass filter is inspired by the way these subspaces form a ladder converging to the space of finite energy function. So, these filters also have some degree of mutual orthogonality amongst them. That's why, this typically what we employ here is what's called an orthogonal filter bank. What I just described, the piecewise constant average and so on, leads to one such orthogonal filter bank called the R multi-resolution R filter bank. Anyway, the impulse response of the linear shift invariant low-pass filter and high-pass filter are related to this so-called scaling and wavelet functions that generate the whole multi-resolution analysis, starting from very coarse going up to very fine. And the beauty is these representations are sparse, that is, most of the energy is concentrated in a few high-value coefficients. So, see, you could also, here we are talking about discrete wavelet transform, you could also use continuous wavelet transform, where the scaling is continuous, the computation is also continuous. And of course, very often, if you do that, then you have a higher fidelity representation. The finer sampling of scale also means more redundant. So one is always compromising between more redundancy and more accurate or more robust representation in a continuous wavelet transform, or a continuous wavelet transform can be differently sampled from dyadic. Dyadic means in powers of 2, like to do in the conventional discrete wavelet transform. You could also be sampling the scales in other ways. Now, see, let's take an example. Here, we first begin with a one-dimensional graph. So let's take an abdominal electrocardiographic ECG. And here you have this abdominal ECG signal, and we have decomposed it using the discrete wavelet transform to get the approximate coefficients and the detailed coefficients. So you can see that the approximate EW coefficient in some sense looks like a crude version of the original signal. They resemble the original signal, but in a crude manner. They seem to be taking plus more than the original signal. The detailed EWP coefficient give you what is missing in this approximation. And therefore, at a given scale, now you can keep doing. You are doing this once. You can decompose this once again into further or fourth scale approximation and the details, but this can continue at many levels as is feasible with the data size that you have. And each time you make this decomposition, what you are doing is to glean out the details that are relevant to that scale. So these are the details relevant to the final scale. And each time you decompose this, you are removing, you are extracting details that are relevant to that scale, both are important. Now let's take a two-dimensional example, something like what Kishore is working on. So, in a separable, see now we are doing this in one dimension, what I showed you in the previous slide, again. Here we were looking at a one-dimensional signal decomposition. But then you could also be doing the same thing on the horizontal and the vertical. That becomes a two-dimensional separable discrete wavelet graph. So what Kishore has done here is to take an example of a brain image, brain magnetic resonance image, and one slice of a brain MR image, and this has been decomposed along the vertical and the horizontal using the DW. And the scheme is shown here on the right to the left side. So each time you do this, what you are doing is you take the approximate and detailed coefficients in the vertical direction, and then the approximate coefficients and detailed coefficients in the horizontal direction. You get four subbands. So from one image, you have four sub-images of 1/4 the size, half size in each direction. This is the so-called LL, or the fourth approximation to this image. And these are the three subbands. You will notice, if you look carefully, that this subband emphasizes the vertical component. This subband emphasizes the horizontal component. And this subband tries to emphasize the diagonal or the graphic components. There are not too many of them in this image, but then you do see some degree of star components coming out more prominently in this subband. Now let's progress from algorithmic analysis to deep learning. You see, past representations using algorithmic analysis are, as you can see, very powerful, very reliable approximations because they are also invertible. You can go back from the algorithmic representation to the original. And if you again once again look back at the image that we saw here, the forced approximation has a close similarity in many realistic images. The forced approximation will have a great resemblance to the original image, and the final subband, the subband of detail, give you specific incremental information. So this is useful in a deep learning context. You see, not only is this invertible, it also separates out features that you want to learn field. So, you see, in a way, when you look at if you were to go to the anatomy of a deep learning structure, so suppose you just blindly let the deep learning structure operate on two-dimensional data, and let it go through many layers, and then once the deep learning structure has converged, and once you see it doing well on unique samples of data, then you may want to go back to what each layer is extracted. And you would find that each layer tends to focus on some specific features. So it has been able to glean out some specific features on which to be able to concentrate with the intent of analyzing those features for further decisions or for further analysis. In a way, that is exactly what you are doing in discrete wavelet transformation. You are gleaning out or separating features of different kinds, incremental features of different kinds, with the intent of simplifying or aiding your interpretation or analysis task. there is a lot of similarities between this hierarchical representation of data in deep convolutional neural network architecture and multi-evolution. DCMN architecture inherently carry out a crude demand. So in a way, a lot of deep learning architectures are intended to do some kind of multi-evolution analysis or some kind of fine and coarse separation in the deep layer, which is often not quite transferred. They learn them organically, learn this representation organically, and what we are trying to suggest is that we should do it consciously rather than trying to force the deep learning structure to reinvent the wheel. Enforcing multi-evolution analysis in deep convolutional neural networks results in a richer knowledge representation of data that allows efficient learning with reduced model count. So, see, what is a deep CNN? It's clearly a set of convolutional layers of systems that learn the hierarchical representation of each amount, directly to data. It repeatedly performs three operations. What are three operations? There's a convolution operation, there's non-linearity added, the convolved output, and then there's pooling the output. Now, look at the similarity between this and what we're doing in the physical math. Convolution and pooling operations in a DCN are empirically similar to the filtering and downsampling operations in a math. So, it provides a suitable framework for identification of code. There's a lot of growth of mRNA-based DCMS in popularity, and they've been used in various applications. For example, biometrics, speech analysis, time series representation, 3D shape analysis, and whatever have you. There is the so-called CAT set. There's a whole class of transforms called the CAT transforms, and the CAT set which implements them. They have shown improvements, they've shown a lot of proprietary work. Includes interpretability or explainability, and they show improvements in network complexity by introducing wavelet functions over the model architecture. Enforcing wavelet-based MRA in DL architectures have often shown to outperform other variants of these architectures which are non-MRA based in terms of performance, complexity, and results. And they've also been observably robust and stable. So what are we trying to do in this work? We are going to look at three examples of biomedical applications. Fetal ECG, non-invasive fetal electrocardiogram, brain MRI image segmentation, and spatial temporal registration of longitudinal brain MRI. Micro-resolution analysis brings excellent time frequency localization. So I said, if you look at many signal processing problems, there is inherent in the problem a desire to work in the natural domain and the transform domain at once. You don't really separate your interaction or engagement with these two domains. You want to see things in the natural domain, also want to see them in the transform domain. And unfortunately, this is limited by what is called the uncertainty principle. The uncertainty principle doesn't allow you to do this beyond a certain point. But micro-resolution analysis is a systematic way of doing it to the best that we can. So intervening wavelets in shallow machine learning and deep learning architecture uses these properties within the network to learn efficient sparse representation of the data. So let's take the first case where we will deal with non-invasive ECG. Our task here is to depict a feature ECG from non-invasive abdominal recording using micro-resolution analysis and machine learning. So let's take a minute to understand what the statistical problem, what is the situation that we are trying to deal with. All of us are aware that when a lady is pregnant, you have two electrocardiograms that are relevant for analysis. One is the mother electrocardiogram, maternal ECG, and the other as the fetus, as the little child evolves in the mother's womb. The fetus also after a point starts exhibiting a heartbeat or heart activity, cardiac activity. The heart of the fetus is also growing and developing. So, the monitoring of the fetal ECG is a way to check the fetal health, to check the well-being of the fetus. Now, this is not a simple problem at all, because any kind of capture of fetal ECGs will always have maternal ECGs interfering. It's an example of, look at it, we have to, what we have to, and we are also worried about the risk, we can't be disturbing the fetus. We can't be causing pain or discomfort to mother, minimize the pain or discomfort to mother. So what we are trying to do here is the role is electronic fetal monitoring. Signals acquired from electrode placed on the mother's abdomen can help us identify and track the fetal ECG. The abdominal signal in the mother consists fetal ECG and maternal ECG and several other noise components. So identifying the very weak signal, fetal ECG signal, from such a heterogeneous mixture is not an easy task. In fact, in a way, the maternal ECG itself is a dominant noise. You may think of it as a noise source, or you may think of it as a highly correlated wave. ECG amplitude is very low, and there is no spectral overlap between the fetal ECG and the maternal ECG. There is also a large amount of variability in record. This depends on the gestation age, the age at which mother is conceiving, and also the age at which the fetus is, how many months the fetus has been in the mother's womb. Fetal presentation, the fetal, where the fetus variance is said to be electrode. Fetal movement, the fetus blossoms and the fetus grows up in the mother's womb. It's not static, it keeps moving. The mother's body mass index and all these things are very significant features that affect the capture that we want. Now, what's the common ways of extracting fetal ECG? One way is that we estimate maternal ECG components using various methods. It could be carbon filtration or another because of neural networks and so on. And we cancel, when we have this combination of maternal ECG and fetal ECG, cancel the maternal ECG from the abdominal signal and do further conditioning processing to obtain clean fetal ECG. Now here, what are the issues that we need to grapple with? Extraction is highly dependent on the quality of the maternal ECG estimation. See, cancellation of a strong signal from the mixture as a strong and weak signal is never easy, because you cannot quite estimate the strong signal to an arbitrary degree of accuracy. You are only assuming that you are estimating the maternal ECG. It's not anyway required to be true. And therefore, if you try to do any kind of subtraction, you are actually sometimes trying to bring in more noise or more distortion. It is difficult to recover signals even after MECG cancellation or SNR recording, so there are many other noise components that indicate. And MECG cancellation can even remove fetal ECG. You think you are removing ECG, then you are also perhaps removing some features of the fetal. So, in all this, deep learning techniques like deep convolutional neural networks and generative adversarial networks, GANs, as we call them, are prompted for MECG estimation. The beauty of these deep learning techniques is that they don't require MECG cancellation. AI techniques can thus deal with signal variability. Unfortunately, the current networks that I use to these tasks are extremely dense and computational. They require a large amount of variable training data, and they are difficult to obtain. It's very difficult to obtain this variable training data. And this technique incorporates the characteristic behavior of non-invasive MECG signals. Let's delve into examples. All factors interfere in our ability to do this task well. So, Nitin, the PhD student Nitin, has been looking at some ways to deal with these problems. So, the first approach that we have used is to exploit the characteristic spectral behavior of non-invasive fetal ECG signals to build sparse time frequency representations of SECT components, ECT components. Here, non-invasive ECT recording. So one typical data set we call the ADSB ECT data set. And this is kind of standardized data set which can be used for testing an algorithm for ECT characterization. And here the first step is to do a pre-processing, which involves normalization of dispute and instoring, and then you generate what is called a scaleogram. On a scaleogram, the vertical axis indicates different frequency bands, and the horizontal axis indicates different time zones. So these are two examples of scalograms that we have generated after the intro. Now, the generated scalograms are then subjected to feature extraction classification. And, specifically, Nitin has discussed what are called the Westnet 50 detailed architecture, followed by multi-layer versus bond, and then he classifies into feature or non-feature. That's essentially we're trying to detect from the scaleogram. Look at this, scaleogram. Let's take a minute to understand the term scaleogram. Scaleogram means essentially a time scale representation. In a discrete wavelength transform or discrete wavelength decomposition, we are essentially replacing frequency bands with scales. So different scales of the discrete wavelength transform actually correspond to different frequency bands. There is a one-to-one correspondence. And different scales give you features at different levels of detail. The finer scales would essentially be higher frequency bands spread over a larger bandwidth. And coarser scales or coarser features would correspond to lower frequency bands with a smaller band. Now, this scaleogram likes to tell you the way in which the frequency bands evolve in time. So, in different time zones, you might detect the presence of a composed or be able to conclude there is no such. That's the representation here. The way to decide between feature and non-feature. This particular data set which Nitin has worked on is called the ADSB EGBD data set, and the real signal 4-channel recording with a 1 kHz sampling, and there are 5 records from women in labor. And here the reason why we chose this data set is a reference annotations which have been provided. So what kind of pre-processing do you do? You do the 1 Hz to 250 Hz bandpass filter followed by a 50 Hz notch filter to remove the power supply noise followed by zero phase filtering. Now zero phase filtering, zero phase is important if you want to introduce dispersion or phase distortion. And zero phase filtering is best done with a finite impulse response. Then you do a normalization based on the median absolute deviation to account for the noise. Following that, you do a scaleogram generation. So scaleogram generation use the 270 millisecond time window, includes 10 milliseconds overlap at each end in case of the feature QRS. So QRS, the QRS complexes are what characterize electrocardiogram. Electrocardiogram is a pseudo-periodic wave. So it's not periodic, otherwise you would have done simply FSP or something. But pseudo-periodic, and sometimes the variations in different periods are indicated. The scaleogram is computed using a Gabor wave. So this is the scheme. These are examples of how signals look at different scales. You have the dominant signal before pre-processing, you have the dominant signal after pre-processing, and you have after that scaleogram generated on the window. Then you have the subject train, scaleogram has to be fed into a training approach, so we use a total 18,000 scalograms generated and labeled using reference cal ECGs, out of which about 9,000 of them are the feature class, about 8,000 are the non-feature class roughly balanced, and this data set of the generated kilogram is used to train and test the DCME classifier. And in this experiment, we did load a 15 to 3 to 2 train, validate, test ratio. So you need a data set, you always need to separate the data set into some parts which will be used to train, some parts which will be used to validate, and finally some parts which will be used to test ad initio. Now here, the feature extraction and classification is based on what's called transfer learning. So you need to use a pre-trained listener. See, it is clearly difficult to use an architecture which would learn only from the people into the data set. They are too sparse in terms of their ability. You don't have as much data as is required to train a deep learning structure as is needed to do well. So therefore, you need to pre-train. You transfer learning. If you learn in a different context and bring that learning to this context. So you pre-train the best access field to extract which features from the PWC representation, and so here we compare the approach with other state-of-the-art DCME techniques used in the literature, and here are the results. Our method requires only about 10K trainable parameters, which is significantly less than the other known in the literature. The accuracy is comparable, and the precision suffers somewhat. Precision suffers somewhat as compared to WNF. That is the compromise. So then there is economy. There is pure economy without compromising too much in performance. That's the way to look at it. That's the key takeaways from this discussion. Key takeaways are that fast representation can significantly reduce computational cost without significant compromise in performance. Fast time frequency representations are constructed based on signal characteristics, which can lead to better understanding of these convolutional neural network knowledge representations. They use interpretability, reliability, and as you can see to some extent, even wrong. Now, the second application that we're going to look at is brain MR image technique. And for some variety, in some variety in who is talking, I would want to invite my PhD student Kishore to continue the presentation. Here to please be welcome.
Hello everyone. Hello everyone. This is the part of where we work with high-dimensional data. I mean to say the previous system was
Is it audible?
Yes, sir. It is audible. It is audible.
Yeah.
So the frequency case was for two-dimensional systems with the one independent variable where the transform is where we are doing the weighted transform. In this case, we will be looking in for the brain MRI segmentation case. First, we look into two-dimensional slices of MRI images from a three-dimensional. Actual wave MRI is a three-dimensional data, but here in this case, we will be looking at individual slices, means two-dimensional, and we will look into the automatic segmentation using multi-resolution analysis and deep learning. So, the MR image is a non-invasive technique to capture the anatomy of the body part. The segmentation requires to identify, like in the brain case, segmentation requires to identify the different like tissues in the brain. For example, the white matter, gray matter, the cerebrospinal fluid. The standard, so there are some non-deep learning based architectures have been used traditionally, and recently the research has been more focused on the deep learning based models. So we will be focusing on the deep learning based models for automatic segmentation. So this one state of the art is the UNet architecture, which has a encoder-decoder structure where the encoder takes in the input and creates a decimated representation of the input, and the decoder reconstructs to the segmented output. So we'll look into that those types of architectures. And what we're trying to improve here with the vanilla unit type of architecture is the we would like to improve the model complexity, and we would also like to bring in economy and interpretability as well. So this is the segmentation pipeline. So we have train MR images. Now the first task is to remove the unwanted region. For example, just extract the brain and remove the nose, ear, and all the other parts of the head. Just extract the part brain. So this network is that network which is used to generate a brain mask so that you can extract the brain region, which is also in the literature for skull stripping. Skull stripping is the extraction of the brain from the like whole MR of the head. The second part is also a learning model. So first part is a supervised learning model here, and the second part is an unsupervised learning model. Both the models use multi-resolution representations, and the second model is used to segment the brain regions. For example, segment the gray matter, white matter region. So the first part is also a segmentation network which segments the brain region from the whole MRI, and the second part segments the green matter and white matter from the previously segmented brain region. So and this gives the true segmentation. So looking into the first part, which is the brain mass generation model. So we have used the encoder decoder architecture, and we have used the dataset IBSR, the Internet Brain Imagery dataset, and the NFBS dataset for training. And we have used discrete wavelet transform with R wavelets here, and wavelet tuning in this model. So the suppose here suppose here this is the first model. What I mean is the MRI network train is we are representing that as with this notation E. And which is out of mask is generated. So what we have to do is we take how the system works. First we take input the MRI, then it will generate a mask which is the region of interest, and then we will multiply the mask with the input image to get the output. So what I mean by that is so we input this so P is the brain, M is the brain mass, I is the input volume, and this is the element-wise multiplication operator. This is the operative function. So we have this mass generated by the deep learning model. We have this input I. So this input I is fed to the deep learning model to generate the brain mass, and then after that both are multiplied element-wise to get the brain. So this is this one. So this the X is the input, which is I, and then this is the model generating the brain mass. Then again X is here, and there we are doing this multiplication to get this brain. So since we are working with the 2D model, so now the overall MRI is a 3D structure. So we take all the body planes. So if you are familiar with the biomedical terms, then there is the 3 body planes: coronal plane, sagittal plane, and transverse plane. So we do the segmentation individually with all body planes. So what I mean is first we feed the model with the sagittal plane data and generate a brain mass, which is MS. Then we feed the model with the coronal plane data, then we generate this brain mass MC, and similarly for the transverse plane data. And then we do this intersections and unions to generate the ultimate final plane. So after having that brain mass from the model, then now the objective is to get the gray matter and white matter region from that region. So this is the second model where we will feed in that slice, we change that slice of the brain. So this is the brain region. So this is CK here, and S is this model, and YK is the simply segmented region. So this is how. So now the second model what we have done here is we have used an unsupervised learning method. So we do a successive decomposition of the input size using discrete wavelet transform, and then apply scaling clustering to the individual subtypes, and then we define the center. So like after applying the k-means clustering to a subband, we get a, suppose we do a level 4 DWT composition. We apply the k-means clustering to the first to the level 4 subband. Then we get some centroid. We use that centroid as the initialization point for the k-means clustering of the level 3 subband. Then we define we do the k-means clustering, define the centroid, and then repeat the process for the level 2 and then level 1. So we move upward and by defining the centroid. So this is a complete algorithm. How it is done. What I have explained. We first we initialize the cluster count, then we apply the so we do a level 1 to level 5 decomposition, and we get this subbands, so LL1, LL2, LL3, LL4, LL5. Now we apply the k-means to LL5, get the centroids, use these centroids as the initialization point of the k-means clustering for this one, and apply the k-means clustering, and then move that like this, and to get the final cluster. And similarly, we combine. We apply this for all the body traits, and then we combine it into using this form. So the result of the first model, which I mean is this model, the inverse generating model, is this one. We input this type which has unwanted trait features also, and we generate this. So these are the downputs from the IVSR dataset, and these are the predicted marks. So here, one thing to notice here is that the number of parameters. So we compare like our results with the unit also, and with the DWT based unit also. So in the unit, the number of parameters is 121,000 parameters, and the blocks are 191 million blocks. But in the DWT unit, the number of parameters is only 9,000 parameters. So there is significant reduction in the number of parameters, and also there is a reduction in the number of blocks. So this validates that point that I also mentioned. It brings a certain amount of economy into the model. So this is the second case we are seeing it here. And we see there is not much compromise in the IU scores also. IU is intersection of over unit, which is a standard metric for segmentation problem. So this is, and these are from both data sets we have trained in NSPS and LGSR. So we have not put the entire NSPS data set because it is a very big data set. We have put 18 volumes only. Since the IVSR also had 18 volumes, so we kept that same. So here this is one significant point would be noted that we bring a major amount of economy into the model by introducing this wavelet-based architecture. For the second part of the, like this is so for the second network, this is this unsupervised segmentation network. So here, so these results are shown directly without the style fitting, just to emphasize the algorithm, how it is working. So these are the 5 subbands that I was talking about. So this is the original image, level LL1, LL4 and LL5. So first we apply the k-means clustering to this one, we get some centroids, initialize those centroids as the starting point of the k-means clustering for this one, and do the k-means clustering and repeat the process successively up to this one. We initialize more than 3 clusters. So we are interested in 2 clusters only, which is the background and the gray matter and the white matter. But we start with initialize with more than 3 clusters. We apply this method that I have mentioned of the k-means clustering, and they get this cluster. Then we take the top 3 clusters from this one. and we get our final output. So here, this is the background, the black one and the green one. So for now, just ignore this boundary part because we have not applied the, just to demonstrate the algorithm here. So this inside region are the white matter regions, the green ones, and the blue ones are the gray matter. The segmentation is pretty like means it matches with the like groups. We do not have any ground groups, but from visual inspection we can see like we can verify that this matches to an extent to what is the actual means so the input is. So you can compare this one visualize and these two images. So these are some more results from the other two planes. So the blue ones are the gray matter. Ignore the boundary ones that inside in the brain only. The blue ones are the gray matter and these green ones are the white matter. So the complete algorithm, the pipeline that I have mentioned earlier. So now I'm taking everything into an effect. So this is my input slide. This is the output of the first algorithm. The mask is generated. We multiply these two to get this one. So here the first is 10. Then we get the plane and then we apply the segment, the gray matter, white matter, and supervised clustering based segmentation with bit substance here. So here is the code. So this is the complete pipeline that was shown for individual such slicing.
So in fact, before we continue, so these two components are so important.
So in the case of so let's understand like what will be the next step. So suppose we now have this output. So suppose we have now have this segmented output. So now there is a case of issue-temporal registration of longitudinal brain MRI. First, we have to understand what is longitudinal brain MRI. So suppose the case is something like that. Suppose there is a patient. For our group, the data that we have taken is from the ischemia stroke patient who have been treated at AIIMS Delhi, New Delhi, and whose MRI acquisition, whose MRI volumes were acquired over a period of time. For example, the MRI first acquisition was taken maybe today, and the next acquisition taken after a month after some treatment. So, for example, what I mean here is first we take an acquisition of the patient, then treat the patient, then take another acquisition, then treat the patient. These type of acquisitions are called longitudinal brain MRI. So, our objective here is to identify time by looking at these two successive MRI acquisitions. So, to do that, what has been, first we need to do this to complete this stage, which is the spatiotemporal registration of the longitudinal brain MRI. What I mean by that is कि suppose we have this two MRI volumes, there will always be some spatial misalignment in the two acquisitions due to the movement of the head while the acquisition. So there at least some degree of, even though very minor, but there will be some spatial misalignment in the two acquisitions. So first we need to nullify that misalignment and make a common reference frame to compare the two volumes. So this is the objective of this segment of the talk. We will do the spatiotemporal registration. So that nullifying the spatial misalignment is called the spatiotemporal registration. So how we do this? We do here we take from in the first part of the talk we dealt with 1D wavelet transform. The second part we dealt with 2D wavelet transform. But in this part we will be working with directly on the 2D on the 3D MRI. So what I mean is, suppose we have this segmentation for the entire volume, and we have now the entire segmented volume of this MRI. Now we take the entire volume as an input and apply our registration method. So in general, the existing methods, registration methods that exist are rigid registration and non-rigid registration. In rigid registration takes care of the translation their those type of things. In our case, in this is a like human body, there will be no sharing at all. So it's the structure of the brain, means head will be same. So we are only dealing with the translation and the rotation. So we are working with the rigid registration. Yes. So we'll be working with the registration. And this is our, so we have been working with the T1 weighted, so the previous one also for the T1 weighted size. So this is how the algorithm works, overview of the registration. So we start by first segmenting the hard side using a image clustering. So this is great because if we take the entire all the sample points in the entire 3D volume, the computation will be very expensive. So first we need to identify certain points in the entire space which is non-deformable over a short period of time. So that is why this first step we identify the hard side using the skull that so that these are non-deformable over a period of time, maybe for 2-3 months, which is our segment of interest, 2-3 months. So when we do duality 3D complex wavelength transform on those segmented values, then we extend the maximus by making multi-resolution different pairs. So I will put this in the next slide, and then we match those triplets and do a point-to-point correspondence of those triplets and apply this structure algorithm for rotation matrix. Extend the structure algorithm for the translation matrix as well, and then apply this everything, multiply this matrix with the volume to be registered to get our end out. So suppose now we have two volumes. So we identify these type of input pairs, like 2 points in each of the volume. So and then try to match as many number of triplets in the two volumes. For example, by the method that is side combination. After this, so the more the number of matches, the better the number of matches, then the better will be the registration. So now coming to the registration main registration algorithm. So traditionally the search algorithm is a what it finds the rotation matrix R between a given pair of points. So here, so this is R is T cross 3, this is T cross 1, and combine this to get this T. So and they are coordinates of the register terms. So this is how it works. So I'll explain of the math from the next slide. So this is how it works. So first we locate that, so A is our volume, reference volume suppose, the month 0 volume. B is our month third or the volume which needs to be registered. So we first locate the centroid of each of the two volumes. So this is like finding the origin of the common reference point that we are trying to locate to the registration, to this registration. This center is like the origin. So now we center this using by subtracting the centroid. So we for both the values. Then we find this covariance matrix by multiplying the volume to be registered with this. With the reference volume transpose, then we do a SVG decomposition of this covariance matrix to finally get the rotation matrix. So with this SVG decomposition, U and V gives us our rotation matrix. Now, if the determinant of this matrix is negative, then that is the step we do not want. So here we simply negate the negation by multiplying with minus 1. And then finally generate E by using this registration. Now we multiply this metric with the unregistered coordinate to get the registration of the crude registration first. Next we fine tuning this registration by, for example, the misalignment was maybe 10 degrees misalignment was there. So by applying this algorithm, maybe we have got 9 degrees of this. Means we have fixed for the 9 degrees. There is still 1 degree of deviation there. So find that we use this method to nullify that 1 degree also. So it is like a good code that this final step is a good code method where we do a grid search. So we filter by small amount of like 0.1 degree, 0.2 degree plus minus and shift of 0.1 unit. So by unit we mean pixels and 0.2 units, pixels of boxes there. And then apply this thing and then evaluate this NCC and MI. So I'll come to the metric. So to summarize this slide once more. So after doing the food registration, then we do the fine tuning by doing a brute first of with minor incremental steps, and then evaluate the metric. So these are the normalized cross correlation metric. This is what we evaluate for one metric, and this is the mutual information metric, and this sum of the differences. So now to the so some cases are here. So suppose this is my reference value 107, and this is so this we have augmented it by deliberately to just for the illustration sake to a more to some degree of rotation. So this is the volume of the say which needs to be registered. In the first step, we will do a crude clustering so that we get this. So these one are the so here we see a parts there, which are those tissues which is not very deformable over a period of short period of time. So these are my input to the registration algorithm. This part set of input to the registration algorithm. So as I was mentioning, if we take this whole set of points, still less number of points, it makes the computation very expensive. So we take this part set of points. So this is one example where we have done the registration. So this is our image that is to be registered. This is after the fine tuning, and this is a superimposition of the unregistered and the registered volume. So we see that here in this superimposition, almost it is the alignment. So the registration is successful. So that comes in a heat map. So this is the for the unregistered. This is for the unregistered. That is see that this difference is that which needs to be registered, and this is after registration. Similarly, shown for all the three body planes. So I'll superimpose unregistered and registered images. And these are the codes. So we can see that from the registered, so these were the codes. With the extended search algorithm, we get this code. Now after fine tuning, we get this code. So here NCC needs to be improved, MI needs to be improved, and this one needs to be everything needs to be reviewed. So in summary, what we have we saw multi-resolution representation for FUGC with 1D circular favorite transform. For MR segmentation, we saw 2D DWC favorite transform. For MR registration, we do duality complex favorite transform. Now, for the learning, in physical ECG, we use that
The total means economy. The total means economy is the number of parameters to the architecture, making the architecture less complex. Yeah.
Thank you so much.
Any other question?
Somebody else is implies.
My question is related to whenever we use some deep CNNs, for example, unit or ResNet, we have multiple architectures. Some architecture is less complex, someone has more layers. So if I get a specific problem, how do we decide that which exact architecture should we use?
Okay, so my basic one is that he's more knowledgeable about internet than I am, so we have to ask him to answer.
Right.
Can talk to you.
For example, segmentation network, the second part of the
And your Kishore?
Yes, yes, he is audible.
Oh,
So, for example, in the segmentation of the in the second part of the talk that is, so why we have used unit here? Because we need some type of model which creates a representation. So units are encouraged from the type of architecture. So for example, what does an autoencoder do? It takes in an input and representation of the input through that propagation. We don't have to study much about the much about engineering of the model inside, but we can only just keep the autoencoder architecture intact with sufficient number of parameters to have the representation. But now we are trying to do is to use that autoencoder type of architecture same as we use that, I mean to say on body encoder decoder architecture. But our objective is to keep without that taking a similar structure where the number of parameters are very large. So it's like a mold where we can represent our data as we want. So we want to more efficient. So we want to have the same structure but with a reduced number of parameters. So we take the similarity between the autoencoded structure and the discrete Wavelet transform filter band. So both have this downsampling and filtering operations and upsampling and filtering operations in the encoder and the decoder, and both have the perfect reconstruction, that idea of perfect reconstruction. Unify those two methods.
have you answered the question? I think your question was related to choice between units.
Right, sir.
So see, even a unit architecture is not one architecture. Unit also has a lot of variation possible with autoencoder and encoder.
Yes.
One way of getting that diversity is by using different filters. Right? So what people are saying that you can use several different filters as a part of unit. You have a choice of which filter you use as a part of unit.